Hello, good people. Welcome to the next video here about the motion and concepts of position, velocity, acceleration. We're going to get right to number three. Let's think about what they're giving us. Let's think about what they're asking for, and we can make a plan of attack from there. A particle's velocity is given by v of t equals 4t cubed minus 6t squared plus 1. Awesome. The function x of t represents the position of the particle along the x-axis. Find the position of the particle after 3 seconds if x of 0 is equal to 5. Okay, let's think about what we're given. Let's think about what we want. We're given the velocity. They want the position. Specifically, they want the position of the particle after 3 seconds. But they're telling us that x of 0 is equal to 5. So there's a couple of ways we can do this problem. And I'm going to show you the shorter way to do this. I think we agree that we need to do this. If I want to find the position function, then I need to do this with the velocity function, right? I need to take the integral of that. However, I notice that they give me two times. One of them is time 0. Let me do it in a different color here. One of them is time 0. They gave me the position there. And the other one is time 3. And they also give me the position at time 0, which is 5. And then they're looking for the position at time 3. And so this reminds me of some of the work that we had done before that's directly related. And I'm just going to move out of the screen here. That's directly related to the a to b of f prime of t dt is equal to f of b minus f of a, right? So this is the first part of the fundamental theorem that says if I'm taking the integral from on a closed interval here, if I can find the antiderivative of that function, I can substitute the top number, substitute the bottom number, and subtract those function values. Well, what if I do this? What if I tell you, oh, my derivative function is v, the velocity, and the antiderivative of velocity is position. And then instead of a and b, we have 0 and 3, which means I would plug in the top number first and then plug in the bottom number. So that means that I could add this to the other side. And think about what this is telling us. If you know the position at the beginning, the initial position, if you add on the displacement, which is what this is going to find between 0 and 3, you're going to get the position at the end at time 3. So this kind of goes with one of the first ideas that we did when we did the first part of the fundamental theorem, which is I can move. This is what the fundamental theorem says, but if I'm given one of these, I can move it to the other side. And because I can do this on my calculator or by hand, I can do all of this, and it's going to equal what I want. So I don't really have to do what we did before. I'm sorry. I don't have to take the antiderivative, find the c value, and then plug it in. I can just do this all at once. And so that's what I'm going to do. I'm going to say x of 0 plus the integral from 0 to 3 of v of t dt is equal to x of 3. By the way, x of 0 given to us is 5, so I can substitute that 5 right away. And now it becomes a calculator problem because I have 5 plus the integral of this function, which a calculator will do for me with math 9. And together, that's going to give me x of 3. But the reason it works is because they gave me the initial position, x of 0, where I'm starting. And then I'm going to add on the displacement, how much it moved. And that's going to give me where it ends up, the final position. So let's use the calculator to figure that out. So let me open my calculator here. I'll move this over so that I can see the full equation. And then we can just type it in. So this is going to be 5 plus the integral, math 9, from 0 to 3 of v of t. Well, v of t is 4t cubed, boop, minus 6t squared plus 1 dt. In this case, I'm going to use x. Press enter, and I just found my final position. The final position is, or the position at 3 is 35. So this equals 35. And I'm done. Could I have taken the antiderivative here and produced a plus c, and then used this to figure out the c value, and then plugged in 3 to get the position? Yes. But because the fundamental theorem allows me to think of it this way, and because I'm given, if you think of this as 1 part, 2 parts, 3 parts, if you know the values or can find the values of 2 out of the 3 parts, well, then you can calculate the third one pretty easily. And that's how we did part A. Can we do the same thing with part B? Find the position of the particle after 2 seconds if x sub 1 is equal to negative 2. So find the position of the particle after 2 seconds if x sub 1 is equal to negative 2. All right, well, let's see. Can I do the same thing? If I know that I'm starting here at x sub 1, so I know x sub 1, I'm going to add on the displacement from 1 to 2 of this function, then that's going to give me x of 2. Right? Because I have the integral of the velocity from 1 to 2 is equal to the antiderivative, which is the position, evaluated at the top minus evaluated at the bottom, but I added it over. So I'm pretty close to being able to finish this fairly quickly. I'm going to substitute this here because I know that x sub 1 is negative 2. And now this is telling me this is the position at 1. This is the displacement between 1 and 2. So if I put them together, that's going to tell me where it's going to end up at time 2. Easy peasy, mac and cheesy. Let's put it in our calculator and we can figure that out. Negative 2 plus math 9 is going to give us the integral from 1 to 2. We're not starting at 0 this time. And then of the function that we were given. I guess I should have saved that in y1 because I was going to use it more than once here, but I didn't, so I'm just typing it over and press enter. The position is 0. So the position at 2 is 0. That's it. So we're using the fundamental theorem of calculus, which tells us this idea as a quote-unquote shortcut maybe to getting the answer a little bit quicker. Conceptually, though, think about what it's telling us. The initial position plus the change in position, which is the displacement, is equal to the final position in the interval that we're talking about, right? And in this case, for part B, we were talking about the interval between 1 and 2. And so we had the position at 1 plus the change in position between 1 and 2 equals the final position at t equals 2. And then finally, number 4, let's see. What is the total distance traveled by a particle during the first 4 seconds if the particle's velocity function is given by this equation? Show the setup and your work. Show the setup and your work. Okay, so I guess I have to do this by hand. But let's see, the total distance. So total distance means I'm going to have to use the absolute values around my velocity function. So total distance is, let me write it out, total distance is equal to the integral of the absolute value of negative 1.5t plus 3. Let me do that, dt. But it wants it in during the first 4 seconds, so between 0 and 4. Show the setup and your work. Okay, so how do we figure this out? Between 0 and 4. So we're talking about here, 0, and we're talking about here, 4. So only in this window are we concerned. How do I figure this out? Well, if I look at my picture, I notice that these triangles are symmetrical, right? This base is 2, the height is 3. This base is 2, the height is negative 3. Except one's positive and one's negative. So if I were to do this without the absolute values, my answer would be 0 because I would add positive and a negative accumulation. But because I have the absolute value, this triangle is actually going to go, it's going to flip up and I'm actually going to find this area and add it to that. But they're the same area. So why don't I just say, let's find the area of this triangle, 1/2 times the base times the height. But then I'm going to double it because this triangle area is the same as that one. And the absolute value means whatever is on the negative side or under the x-axis, we want it in the positive side. So this shading should be the same size as that one. Maybe not to my drawing, but it should be. And so here I have my answer when I figure this out. These will reduce, so then I'm just left with 6. And this is the total distance that the particle traveled in the time between 0 and 4. Again, let's keep those big ideas in our heads. If I want to go backwards from acceleration to the velocity, take the antiderivative or integral. If I want to go from velocity to to position, take the antiderivative. But also, when I'm taking the integral of velocity, that gives me displacement. Taking the integral of the absolute value of velocity, that gives me total distance. And that's what we were looking at, or that's what we're looking for on number 4.